Section 14.2, double integrals and volumes of solids. So now you're about to see why we were so intent on setting up those double integrals that we had set up in section 14.1 instead of just doing them the way we had done them previously in Calculus 2. And the reason for that is because we have to set up that region in order to find the volume of a solid lying above that region. So let me give you an example of kind of what we're looking at here. Suppose I've got the xy plane. I'm just going to draw it this way. Okay. So I'm going to set this up differently. This will be y and this will be x, because remember we have our z-axis going up. All right, and suppose here I have some solid in the plane, okay, and I'm interested in this solid lying above the region from x equals a to b, and y from c to d. All right, so the region in question is this. So I'll see if I can dust this gently with this gray, make it not too hard to see. And the idea is that I've got some solid function here, and it's lying above the plane. So maybe I have something that looks like this. Come up to it, come up to it, come up to it, come up to it, and whatever that looks like, maybe it looks like that, right? Actually, undo that. Maybe it looks like that. So we've got our surface of our solid here in green. It kind of takes on this shape. And then we've got the volume underneath that surface, between this surface and the xy plane. So that's what we're interested in finding. And it's not just a length times width times height situation, because the surface is not necessarily parallel to the xy plane. As you can see here, the surface is clearly not parallel. I hope it's clearly not parallel. And our job is going to be to find the volume of this little slice of this solid that we're dealing with, right? So the region in the xy plane that we're looking at is our region R, right? So we're looking for this volume. Now, if this, well, yeah, we can go ahead and set this up. So our volume is going to be equal to our function f of xy. So we're going to assume this solid is given by f of xy. And then we're going to multiply that by the change in x and the change in y. Okay, so for any tiny little parallelepiped, any tiny little prism, if you will, out of this, that's what we would have, right? That's exactly what we would have. So we would have our little parallelepiped or prism here, and we would estimate this, we would find this volume in this way, where we have our delta x and our delta y and running across, and then we could find that. Okay, but because this is going to be done over the entire surface, we would find that our volume is equal to the integral from a to b of the integral from c to d of our function f of xy, integrated first with respect to y, then with respect to x. Okay, so this is equal to the double integral over the region R of f of xy dA. So with respect to the area of the region R. All right, so dA is just dx dy. Like that's what dA is. The challenge for us is coming up with the region. How do we describe the region? It's not always going to be a rectangle in the xy plane. It could be over a circle in the xy plane. It could be over a region bounded by multiple curves, as we've seen in the past. So the region itself and identifying the region is half the battle of setting these guys up. All right, so now that you kind of have a picture of what it is that we're going for, let's go ahead and define our double integral. All right, so our double integral, if f is defined on a closed, let me write this down, if f is defined on a closed bounded region R in the xy plane, then the double integral of f over R, that's how we read it, is the double integral of f of xy over r dA, okay, that's equal to the limit, there we go, as delta goes to 0 of I equals 1 to infinity f of x sub I, y sub I, so our initial values of x, y, delta a sub I. Okay, and what this is giving us, it's giving us, so I'll write it this way, it's giving us that volume under the surface lying above the region R. So it's going to be the volume of the solid, sorry, not surface, of the solid lying above the region R. Okay, that's the whole point of this. It's going to tell us, that's better, it's going to tell us what is the volume of that. Okay, so this is going to be just like the iterated integrals we saw in section 14.1. The only difference is now we have a function inside of our integral. It's not just the area. We're going into that third dimension. So this is going to be the integral over R of f of xy dA. That's going to be our integral from a to b of our integral from g2 of x to g1 of x of f of xy dy dx. So hopefully if you can see, if you just took out the f of xy, we'd be looking at the area of the region, right? The only difference is now we're integrating that solid, whatever's giving us that solid, we're integrating that over that region. You know what? Put a box around that whole thing. There we go. So let's do an example. Okay, so let's find the volume. Find the volume of the solid formed by f of xy equal to 8 minus 2x squared minus y squared for x between 0 and 1 and y between 0 and 2. Okay, so we've got a rectangle in the plane where x goes from 0 to 1 and y goes from 0 to 2, and then we are integrating with this solid over that region formed by that x and y. So here we go. Our volume is equal to our integral from, so x values first, 0 to 1, y values second, 0 to 2, of f of xy is 8 minus 2x squared minus y squared. Integrate first with respect to y, then with respect to x. So let's go ahead and set it up. Let's go ahead and evaluate it. We have it set up. So our integral from 0 to 1 of. So now notice I'm integrating with respect to y. So this is going to be 8y minus 2x squared y minus 1/3 y cubed evaluated from 0 to 2 and then integrated with respect to x. So let's evaluate that inner integral. Integral from 0 to 1. So putting in a 2, I'm going to get 16 minus 2x squared times 2 would be 4x squared. Remember, these are y values. We are only going to substitute them in for y's. Okay, minus, and then I put a 2 here, I get 8/3. Oops. Minus, now I put in a 0 for every y. This goes to 0, this goes to 0, this goes to 0. So we're just subtracting 0. Okay, and our result, it gets integrated with respect to x. So that's the integral from 0 to 1. 16 minus 8/3. So 16 times 3 is 48, minus 8 is 40/3, minus 4x squared, and we integrate that with respect to x. Great. So we can do that. So this is going to be 40/3 x minus 4/3 x cubed, evaluated from 0 to 1. Putting in a 1, we get 40/3 minus 4/3. Putting in a 0, we get 0, so minus 0. So this is going to become 36/3, which is equal to 12. And if we had been given any kind of units for this, it would be 12 units cubed. So in any kind of application problem with measurements, we would want to make sure to include those units. Okay, so let's do one that's a little more complicated. Another example here. Let's find the volume of the solid formed by the planes z equal to 0, y equal to 0, y equal to x, and x equal to 1, and the surface f of xy equal to e to the negative x squared. Okay, so the planes z equal to 0 and y equal to 0 are the xy and the xz coordinate planes respectively. So I'm going to go ahead and draw this. All right, so we have our planes. There we go. There. Okay, so we have those two planes in place. Then we have got y equal to x. So where y is equal to x is going to actually come straight out this way, and it's going to give us another plane here. All right. So here we have it. So we're kind of sitting in this triangle, triangular prism right there. And then we have also x equal to 1. So I can come out here to 1, and this would generate another plane. Okay, parallel to the to the YZ plane. Okay, so I'm working with this, and it's bounded here. So if I'm looking at the XY plane, I'm bounded here, and then it goes straight up in the Z direction from here. So again, hopefully you can see that we are narrowing this down to this triangular prism, and that's the space that we're kind of working in. Okay, and then we were asked to find the volume of the region bounded by these planes and e to the negative x squared. Well, e to the negative x squared, that does not contain a y in it. So this is going to run parallel to the y-axis. So it's just going to give us this curve. It's going to look like this. It's going to have that decay shape to it. So it's going to go through the point 0, 0, 1. It's going to have that decay shape to it. At x equal to 1, it goes through the point 1 over e. So that's my z value there. Here I have z equal to 1. Okay, so then I'm getting this, and this is just going to be, you know, just run across. And so what it's going to look like in this plane, it's really just kind of a, well, kind of like a circus tent, I do believe. So you can kind of see what I got going on there, and then it's coming back. So if I were to draw this again, just kind of externally, just to get a feel for what it looks like, it's something like this. Okay, where these guys in the back are kind of pushed away from us. Can make that look a little cleaner. There, something like that. So that's kind of what we're dealing with as far as our shape is going to go. So now what we have to figure out then is, okay, well, how do we describe this region R? So let me get out a lovely blue here. This region R in the plane, and that's how we're going to have to figure out how to set this thing up. Well, x goes from 0 to 1. So we're going to integrate this. We have our integral. I'm going to go dy dx. So the first integral is all x values, and those are going to be constant values, and then we'll figure out the y value. Okay, so for the x values, x is going from 0 here out to 1 here. Okay, so that's how x is going. We're going from 0 to 1. So 0 to 1. Now the y value, it starts at 0, which is here, and it goes along until it hits y equal to x. So we begin at 0, this is our y, and we go up to x. So these are our boundaries, 0 to 1 on x, 0 to x with respect to y. And then we put in our function, which is giving us the top of our solid. So that's going to be e to the negative x squared. All right, so first things first, let's integrate this with respect to y. Well, this is our v, by the way, for volume. So v is equal to our integral from 0 to 1 of, and we integrate this with respect to y. Now, e to the negative x squared is not an easy integral to find with respect to x, but it's very easy to find with respect to y. There's no y there, so it's constant. So this is just e to the negative x squared times y, and we evaluate that from 0 to x. And then the result is integrated with respect to x. So this is our integral from 0 to 1 of x e to the negative x squared minus, plugging in a 0 for y makes that 0, so minus 0 dx. Now this we can integrate fairly easily with a u substitution. So let's have u be equal to negative x squared, then du is negative 2x dx, which means x dx will be replaced with, divide the negative 2, we get negative 1/2 du. So we'll make a substitution for x dx. So this becomes our integral from 0 to 1. It's not 0 to 1 anymore, though, because we're integrating with respect to u now. So integrating from, we'll change the boundaries back in a moment. If you wanted to change the boundaries now, we've got u at 0, that would be negative 0 squared, which is 0, and at 1, that would be negative 1 squared, which is equal to negative 1. So we'd be integrating this from 0 to negative 1 if we're doing that with respect to u, but I'll switch back to x's at the end, and then we'll just switch our boundaries back to x boundaries. Okay, where were we? Yes, so u substitution. So this is going to be negative 1/2 e to the u du. So we've substituted x dx with negative 1/2 du, and e to the negative x squared becomes e to the u. So this is negative 1/2 e to the u. I would say plus a constant, except we're not. We're evaluating this at specific boundaries. So negative 1/2 e to the negative x squared evaluated from 0 to 1. So that's going to be negative 1/2 e to the negative 1 minus negative 1/2 e to the 0. E to the 0 is 1. So this is negative 1/2, 1 over 2e, I should say, because the e will go into the denominator, plus 1/2 times 1 is 1/2. So there we have it. Over 2. So there we have it. We can combine that if we wanted to by multiplying an e to the numerator and denominator of the second fraction. So that'll be negative 1 plus e over 2e, or e minus 1 over 2e. This negative is part of that one. There we go. All right, so there we have it. There's our final answer. And let's see. What did we have to do to get here? So what we had to do, first of all, was we needed to go ahead and sketch the region. It's not always easy to do, especially in R3, but that's part of the reason we worked so hard to develop those skills earlier in the course. So we do need to sketch it so we can get a feeling for what we're working on. Otherwise, it's very difficult to see where our boundaries lie. But here we could see that our boundaries on x went from x equal to 0 to x equal to 1. Our boundaries on y went from y equal to 0 to y equal to x. All right, and then z goes up to the function, the surface of the solid in question. And then once you have the integral set up, the actual work is usually relatively straightforward. Now on your exam, I am going to ask you to show the work that you're doing for this, because it's very important that you know how to do these integrals like this. And there are some very good programs out there that will do multiple integrals for you. Symbolab has a good calculator, for example. But for the purposes of our course and for this test, it's very important that you get it set up correctly and work it in the correct order, integrate correctly. So I will be asking you to show this work on your next exam. Okay, so let's now talk about the properties of double integrals, and let's do that in a color that's easier to read. There we go. Properties of integrals. Okay, they're the same properties that we're seeing in integrals all the time. So number 1, given the double integral over r of a constant times a function integrated over an area, that is going to be equal to the constant times the integral. So the integral just comes right out. I'm sorry, the constant comes right out of the integral. So same old there. Same thing for the sum or difference of functions. If we have our integral over our region R of f of x plus or minus g over a, that's just going to be equal to the sum of the integrals. Alrighty. Third, if you have got a function, it's going to be greater than or equal to 0 if and only if the function itself is greater than 0, right? So if you recall, this is analogous. I'm just going to sketch this really quickly. This is analogous to the following. This has a positive integral, right? But if I drew that same curve kind of underneath, I would get this, which would be a negative of the same integral, right? So it's the same concept here. So let me get rid of all that. We don't need that. It's just a visual to help you understand what I just said, what that meant. So here we go. If we have the integral over r of f of x, y, dA, that's going to be greater than or equal to 0 if and only if, all right, so IFF for if and only if, for the double bar arrow, f of x, y is greater than 0. Okay. We have the same situation with functions being above and below each other. So number 4, if we have our double integral over r of f of x, y, dA, that is going to be greater than or equal to the double integral over r of g of x, y, dA, for g, no, let me rephrase, for f of x, y greater than or equal to g of x, y greater than or equal to 0. Okay, so we want to make sure our functions are stacking properly. 5, we've got our double integral over r of f of x, y dA equal to the integral over r 1 of fxy dA plus the double integral over r2 of f of xy dA, given that our region R is equal to the union of R1 and R2. Do better than that. R1 and R2. Okay, so just like what we saw in that first example, we can split regions up, or it was in the example previous in section 14.1, but we can split these regions up as needed and then add the volumes together to help us get a better angle on some of these. Okay, and the last thing I'm going to give you for this section is a theorem. So this is Fubini's theorem. Okay, I'm going to give you the first half of it. The second half is if you were to change the order of integration, which is the exact same thing. So let f be continuous on a plane region R. Okay, then if R is defined by x between a and b and y between two functions of x, g1 of x less than or equal to y less than or equal to g2 of x, where g1 and g2 are continuous, where g1 and g2 are continuous on our interval, continuous on a to b. Okay, then the integral over r of f of x, y over with respect to the area is equal to the integral from a to b of the integral g1 of x to g2 of x of fxy dy dx. And I will put a lovely box around that, and that's exactly what we've seen previously as well. Okay, so that'll wrap this one up. If you have any questions, as always, please let me know.